last lecture, we have seen convergence of improper integrals of type A. Okay. Now we will see convergence of the integrals of type B. If you remember, the type B improper integrals are nothing but the integrals in which the function or the integrand is become infinite on the range, okay, on the given range. So the test for convergence of the integrals type B, so we will see in some cases, okay. So case 1, okay, for example, suppose this integration I, okay, is equal to integration from A to B of f of x, okay. Suppose this is the improper integrals of type B. Since it is improper integral of type B, this integrand f of x must becomes unbounded or become infinite in the given range. Suppose x is equal to a, that is lower limit point is the only singular point. Singular point means this function or integrand becomes unbounded or become infinite at that point. Okay, that point is said to be singular point. Okay, so case first. Okay, case first, the point x is equal to a or lower limit is the only singular point. Okay, is only singular point, okay, of this f of x. Okay. So in this case, the improper integral I from a to b f of x dx. Now since x is equal to a singular point, this means f of a or f of a plus, that is if it tends to a from right side, then function become unbounded, okay, plus or minus infinity. This point a is said to be singular point and function become unbounded. So since we assume that left end point or this lower left limit is the singular point, so function become unbounded at that point. Okay, so this integration is equal to limit epsilon tends to 0 from right side to 0 plus integration from, now instead of a we will write a plus epsilon and b as it is, okay, f of x. Now if this value is exist and finite, then we say that this improper integral is convergent, and this value is the point to which the integration is convergent. Okay, what we have done, a is singular point, so we have taken limit epsilon tend to 0 plus of a plus epsilon. Now here instead of a you are taken a plus epsilon, where epsilon tends to 0 from right side. Okay. This is the definition of convergence for improper integral when this point a or lower limit is the singular point. Okay. Now similarly, if b is the upper limit, or we can say right hand limit b is the singular point. Okay, so we taken case 2. If the right hand limit or upper hand limit b, if x is equal to b, is singular point. Okay, so in this case the function become unbounded. Okay, because it is a singular point. So in this case, the integration from a to b of the function is convergent if limit epsilon tends to 0. Now there is no problem in this limit a. The problem is with b. So if limit epsilon tends to 0 of b minus epsilon, okay, of b minus epsilon, instead of b we are taking b minus epsilon and epsilon tends to 0, from right side of the function f of x. If this value exists and finite, then means that this improper integral is convergent. Okay. So when this value exists and is finite, then this improper integral is said to be convergent. Okay. Now from these two cases, we will make some observation about case third. What is the case third? If the singular point is not A and not B, but a point in between A and B. Okay. If C belongs to AB, is singular point. Then how to check convergence of the integral? Now we know since C is the point between A and B, divide this integration into two parts. Okay. So divide the integration from A to B into two parts. The first part is from A to that singular point C, and the other part from that singular point to the upper end B. Okay. Now we can check the convergence of this part using case 2, because here upper end point is singular point, and we can check the convergence of this part using this case 1, because here this lower limit is the singular point. So if both the parts are convergent, then the improper integral from A to B is said to be convergent. The case 1. Okay. Now we will see now the first and important case. Okay, about convergence of the improper integral. Okay. Now we will see case 4. So case 4, in this case, this is the improper integrals of type B such that both the limits upper and lower A and B are the singular points of this function or integer f of x. Okay. So here both A and B are the singular points. Okay. So function become unbounded when x tends to A or x tends to B. So in this case, this improper integral is convergent if this integration we can write as f of x dx is equal to limit epsilon tends to 0 plus and delta tends to 0 plus. Now here from previous definition we can construct the definition for these two for this improper integral where both the endpoints or limits are the singular points. Okay. So here A is singular point, so we can write A plus epsilon tends to 0 plus, and B is a singular point, so B minus the delta and delta into 0 plus of the function f of x. Now if this value exists and finite real number, then we can say that this improper integral is convergent and converges to this value. So this value is equal to real number, then this improper integral is converges to this real number. Okay. Now we will see some examples of improper integrals of type B, and we will check whether the given improper integral is convergent or not. Okay. We will see some examples. Okay. So first example is to check the convergence of improper integral dx upon x cube. Okay. We can take any example. Okay. So why this is improper integrals of type B? Because here integrand, that is function, is 1 upon x cube, and the 1 upon x cube is unbounded and x is equal to 0. This lower end point is the singular point for the function 1 upon x cube. So this implies this integration is improper, and improper integral of type B because the integrand or function becomes unbounded at the limit left end limit 0. Okay. So we have seen the definition. So to check whether this improper integral is convergence or not, we know this integration is equal to limit epsilon tends to 0 plus, okay, epsilon tends to 0 plus of, now instead of 0 we write 0 plus epsilon. Okay, we know here is a, we write a plus epsilon, and upper limit there is no problem, it was not singular point, so as it is 1 and dx upon cube. Okay, so if this value is exists as of it is some finite real number, then we say that this improper integral is convergent to that real number. So this is equal to limit epsilon tends to 0 plus, we know the integration of dx upon x cube, so we can write 1 upon x cube as x to the power minus 3 dx, and limits from 0 plus epsilon is same as just epsilon and 1. Okay, this is equal to limit epsilon tends to 0 plus the integration of x to the power minus 3 is nothing but x to the power minus 3 plus 1 upon minus 3 plus 1. So x to the power minus 3 plus 1, that is minus 2 upon minus 3 plus 1, that is minus 2, and limits from epsilon to 1. This is equal to limit epsilon tends to 0 plus, now put first x is equal to 1, so it's 1 raised to the power minus 2. If you put x is equal to 1, so we get 1 raised to the power minus 2, which is equal to 1, and this is 1 upon minus 1 by 2, so this is minus 1 by 2. Now minus, put x is equal to epsilon, so epsilon raised to the power minus 2, that is 1 upon epsilon square, and this is again minus 2, so plus, so minus minus become plus 1 by 2 as it is, and epsilon raised to the power minus 2, so 1 upon epsilon square. Okay, now as epsilon tends to 0, epsilon square also tends to 0, which is epsilon, okay, epsilon square also tends to 0, so 1 upon 0 tends to infinity, so total value tends to infinity. This implies this improper integral is not convergent, that is divergent, and diverges to plus infinity. Okay, this is the use of this definition to check whether the improper integral is convergent or not. Okay? Now we will see another example to check the convergence of the improper integral. So integration is from 0 to 1 and dx upon square root of 1 minus x square. Okay. Now what is the singular point here? This is the improper integrals of type B, so there must be some singular point. The singular point is x is equal to 1, because as x is equal to 1, x square also equal to 1, 1 minus 1 0, so denominator becomes 0, so the function is not defined. This implies function becomes unbounded and x is equal to 1. This is the improper integrals of type B, and this point 1 is the singular point. So again we know this integration is equal to limit epsilon tends to 0 plus, that is from positive side. Okay, now here there is no problem with 0, 0 is not singular point, input x is equal to 0, so dx upon square root of 1, so dx upon 1, so only dx remains. Okay, so function is defined, not bounded that x is equal to 0. Okay, so only singular point is this upper end limit point, okay, 1. So limit epsilon tends to 0 plus, now instead of 1 we write, you know, it is here is b, then we write here b minus epsilon, so here it is 1, so 1 minus epsilon, and the integral is 1 upon square root of 1 minus x square into dx. Okay, now we know the integration of 1 upon square root of 1 minus x square is sin inverse x. This is equal to limit epsilon tends to 0 plus, this integration is sin inverse x, and limits from 0 to 1 minus epsilon. Okay, so this is equal to limit epsilon tends to 0 plus, now put upper limit, so sin inverse of x is equal to, put 1 minus epsilon minus sin inverse 0, but sin inverse 0 is 0, so no need to write this value, so only limit epsilon tends to 0 plus sin inverse of 1 minus epsilon. So epsilon tends to 0 plus, 1 minus epsilon tends to 1. This implies this value tends to sin inverse of 1, and sin inverse of 1 is equal to pi by 2. Okay. This is some finite real number. This implies this improper integral is convergent and converges to pi by. Okay. We have seen test T1 and T2, which correspond to the test integrals for the integrals of type T. Now we will see test integral of the second kind, that is test integral for integrals or improper integrals of type B. So first test, now T1 T2 has already done. Now we will see T3 and T4. Okay. So test T3 is the integration of 1 upon x minus a raised to power b with respect to x from a to b, where a is singular point, is convergent if p is less than 1 and divergent if p is greater or equal to 1. So what we will do? We will do just what we know. Just know the definition of convergence of the improper integrals of type p. We will use it here. Just okay. So the integrals, improper integrals, where this a is singular point, so integrals from a to b, so dx upon x minus a raised to power p. Okay. Now we know this integration is convergent if the value, we know this integration is equal to limit epsilon tends to 0 plus, because this a is singular point. Okay. A plus epsilon to b of dx x minus a raised to power b. This value exists. Okay, and has some, this value is equal to some finite real number. Then this improper integral is convergent. Okay. Now so we will calculate limit of this integration. So first we will calculate this integration, and then we will take limits. Okay. So now integration from a plus epsilon to b of dx upon x minus a raised to power p is equal to integration from a plus epsilon to b. So we can write x minus a raised to power p as x minus a raised to power. So denominator when it goes to numerator, raised to power p becomes raised to power minus p into dx. This integration is equal to a plus epsilon to b. So x is minus a raised to power minus p plus 1, that is 1 minus p, upon minus p plus 1, that is 1 minus p. Okay. Now we don't have to write this integration like this. Okay. We don't need to write the integration sign. Just put now limits, lower limit is a plus epsilon, upper limit is b. Okay. This value is equal to this. So we will take now a limit of this integration. This integration is equal to this. Okay. So limit epsilon tends to 0 plus of this integration, nothing but this integration, nothing but equal to this part. So we will put first here. We will put limit also. Okay. So put x is equal to b. So this becomes b minus a raised to power 1 minus p upon 1 minus p minus, put x is equal to a plus epsilon. So a plus epsilon minus a, so remains only epsilon. So epsilon raised to power 1 minus p upon 1 minus p. So limit of this integration nothing but limit of this value. So limit epsilon tends to 0 plus b minus a raised to power 1 minus p upon 1 minus p minus epsilon raised to power 1 minus p upon 1 minus. Now epsilon is into 0 plus. So but in this term there is no epsilon. So this is constant for this limit. So limit of this term is equal to same value. Okay. So this is equal to b minus a raised to power 1 minus p upon 1 minus p as it is, minus again 1 upon 1 minus p as it is. So limit epsilon tends to 0 plus applies to only this term, epsilon raised to power 1 minus. Okay. Now we know limit epsilon tends to 0 plus epsilon raised to power x. If this x is positive, okay, like x raised to power epsilon raised to power 1, epsilon square, epsilon cube, then epsilon tend to 0, epsilon raised to power 2 also tends to 0. Since epsilon tends to 0, epsilon square also tends to 0. Okay, so this, if this x is positive, then limit epsilon tends to 0, epsilon raised to power x is also equal to 0. But if this x is negative, okay, so then limit epsilon tends to 0, so epsilon x is equal to suppose minus 2. Okay, so this is equal to limit epsilon tends to 0 plus, so epsilon raised to power minus 2 is 1 upon epsilon square, as epsilon tends to 0, 1 upon epsilon says 1 upon epsilon square tends to infinity, so limit becomes infinity. So epsilon raised to power x, if x is positive, limit is 0, if x is negative, limit is infinite. Okay, so we will use this concept here. Okay, so if 1 minus p is greater than 0, this limit is equal to 0. You have just see, if the value of epsilon raised to power x is positive, then limit equal to 0. So this limit is equal to, this is as it is, b minus a raised to power 1 minus p upon 1 minus p minus 1 upon 1 minus p. If 1 minus p is greater than 0, then limit is equal to 0. So 0 into 1 upon 1 minus p is equal to 0. So value is equal to only this. But when 1 minus p is positive, but 1 minus p greater than 0 means 1 is greater than p, that is p is less than 1. So when p is less than 1, limit equal to this. But when 1 minus p is negative, this limit is equal to infinite. This is some finite number, this is some infinite number, so total number is equal to some infinite. Okay, so when 1 minus p is less than 0, that is p is greater than 1. Okay, so for p less than 1, this limit exists and finite, and for p greater than 1, this limit is infinite. So we have observe one thing, this integral is convergent if p is less than 1 and divergent when p is greater than 1. But what about p is equal to 1? We will see now. Okay, so for p is equal to 1, this limit will becomes limit epsilon tends to 0 plus integration from a plus epsilon to b, okay, dx upon x minus a raised to power p, but p is equal to what? So only dx upon x minus a, dx upon x minus a. This is equal to limit epsilon tends to 0 plus integration of dx upon x minus a, log of x minus a, log of x minus a, and limits from a plus epsilon to b. So this is equal to limit epsilon tends to 0 of positive sides, put first x is equal to b, so log of b minus a minus, now put x is equal to a plus epsilon, so minus log of x is equal to a plus epsilon, so a plus epsilon minus a, so remains only log of epsilon. Okay, but as epsilon tends to 0 plus, log epsilon tends to infinity, so this total value tends to infinity. So this implies the integral is divergent for p is equal to 1. So this integral is convergent when p is less than 1 and divergent for p greater than 1 and for p is equal to 1. So divergent for p greater than equal to 1. This is the integral test T3. Okay. So another test T4, very similar to the another first test we have seen. So test T4 is to show the integral from a to b of dx upon b minus n raised to power p is convergent when p is less than 1 and divergent for p greater than equal to 1. Now we can easily see that here if you put x is equal to b, b minus b then becomes 0. So this integrand becomes unbounded at the point b. So here b is singular point. So we have to check the convergence of this integrals of type b. We know the definition when upper limit is singular point. Okay, here b. Okay, so we have noted it by minus sign. Okay, b minus, don't mean minus b. Okay, so b minus means here b is the singular points of this integrand. So this integrand nothing but equal to limit epsilon tends to 0 plus Now b minus epsilon and a as it is of dx upon b minus x to the power p. But 1 upon b minus x to the power p means b minus x to the power minus p. Okay. So limit this value as it is a to b minus epsilon, and this we can write like this. Okay. Now integration of this is b minus x to the power minus p plus 1, that is 1 minus p, upon minus p plus 4, that is 1 minus p. And limits from a to b minus c. So if you put limits, put x is equal to b minus epsilon. So b minus b minus epsilon. So b and b get cancelled. So only remain minus of minus plus epsilon raised to power 1 minus p upon 1 minus p, minus put x is equal to a. So b minus a raised to power 1 minus p upon 1 minus p. Now again, as we seen previously, limit epsilon tends to 0 plus. If this 1 minus p is positive, then limit of epsilon raised to power 1 minus p and epsilon tends to 0 becomes 0. So only remaining part is minus of b minus raised to power 1 minus p upon 1 minus p. But minus of 1 minus p we can write as b minus 1. So limit is equal to b minus a raised to power 1 minus p upon b minus 1. Okay. And if 1 minus p is negative, then limit epsilon raised to power raised to 0 plus of epsilon raised to power 1 minus p is infinite. We already seen. So this becomes infinite. So for 1 minus p less than 0, limit is infinite. This implies when p is less than 1, the integral is convergent, and for p greater than 1, the integral is divergent. And what happened for p is equal to 1? I left it to you. You solve for p is equal to 1, and you will get this improper integral is also divergent for p is equal to 1. Okay. I explained this in very short because you already seen 2-3 tests of this type. Okay. So it is very simple to understand. Okay. Thank you.